Welcome back. Now we'll move on to the next article, that is springs in series and springs in parallel. The VTU questions related to this article goes like this. Derive an expression for effective spring constant for a series and parallel combination of springs. Okay, we shall derive an expression for effective spring constants in series and parallel combination. Okay, so first we shall start with the series combination. You have to write this diagram there. So consider two springs which are connected in series. Let S1 and S2 are the springs there. So K1 and K2 are the spring constant of spring S1 and S2 respectively. They are in series now. Okay, so when you connect a load for these two springs which are connected in series there, so there will be an extension produced in the spring. Let the total extension produced in the spring shall be X. Okay, and separately there will be extension in the spring S1 as well as what? S2 there. Let X1 be the extension produced in the spring S1 and X2 shall be extension produced in the spring S2 there. Okay, so you know that X is equal to X1 plus X2. The total extension produced in the spring, total spring system, is equal to extension produced in the spring S1 plus extension produced in the spring S2 there. Okay, so when you connect the load, what will happen? So there will be a force, deforming force acting on a body. Okay, so F is equal to mg. Okay, m is the mass there, F is equal to mg. So when it is in equilibrium position, when it is not moving there, so there will be a equal and opposite force, restoring force acting on this spring system there. Okay, so it is equivalent to F is equal to mg, F in the upward direction there. So this restoring force, which is equal to mg, so will be acting on both the springs. That means restoring force on the spring S1 is same as restoring force in the spring S2 there. Okay, in the both the spring, restoring force will be same there. So this is the key point in springs in series there. So total increase in the length of the spring is given by X is equal to X1 plus S2. Already noted that. Take it as equation number 1. Now restoring force in the spring S1 and S2 are same there, because so the total restoring force acting on the spring is same as S1 as well as what? S2 there. Okay, the restoring force in the spring S1 and S2 are same. Okay, so restoring force in spring S1 is given by, so is equal to what? Mg. Restoring force is equal to mg there. Okay, because it is equal and opposite there. F is equal to mg, and you know that restoring force is proportional to displacement. In the first spring, what is the displacement there? X1. It is proportional to x1. So proportionally constant. What is this? Spring constant K1. K1 is the spring constant of spring S1 there. Similarly for the spring S2 there, here also restoring force is same there. In the both springs, restoring force will be same there. So F is equal to mg and is proportional to displacement. Okay, and proportionality constant is K2, spring constant of spring S2 there. Okay, so now from this equation I can get x1 is equal to mg divided by K1. So from this equation I can get x2 is equal to mg divided by K2 there. Okay, now if K is the Ks is the equivalent spring constant of springs in series combination there. Okay, and it must be equal to mg, because restoring force in both the spring will be same. Okay, therefore F is equal to mg must be equal to proportional to what? Displacement. What is the displacement here? X is the total displacement of the spring system, and it's a proportionality constant Ks. Okay, equivalent spring constant in series combination. Okay, so everywhere minus should be there. Since everywhere minus comes, I can neglect minus there. So Ks there. So from this equation I can get X here. X is equal to mg divided by Ks. So I got x1, x2 and x. Substitute in the main equation, equation number 1. So I got x1, x2 and x. Substitute in the main equation. So what I will get? Mg divided by Ks is equal to mg divided by K1 plus mg divided by K2. Okay, mg get cancels there. 1 upon Ks is equal to 1 upon K1 plus 1 upon K2. Or you can take Ks is equal to K1 plus K2. Ks is equal to K1 K2 divided by K1 plus K2 there. That means in series combination, equivalent spring constant decreases there. It is less than any one of the spring there. Okay, this is about series combination. The point to be noted here is the restoring force in the both the springs will be same. Okay, but the total extension produced is equal to extension produced in the spring S1 plus extension produced in the spring S2 there. This point to be noted there. So the case will be reversed when the springs are in parallel combination. There will move on to springs in parallel now. Springs in parallel. So this is a parallel combination. As usual, there are two springs S1 and S2 with spring constant K1 and K2. They are in parallel now. a mass is connected there. So when you connect the mass, there will be an extension there. So let the extension produced is equal to x. That means x is the displacement produced in the mass. That means extension produced in both spring S1 and S2. But point to be noted here is extension produced, since they are in parallel combination, the extension produced in the both the springs will be same. Okay, it is x. That means total extension produced in the spring system is same as extension produced in the spring S1 as well as what? S2 there. But point to be noted here is the restoring force. What is the downward force that is acting there? F is equal to mg. When it's in equilibrium position, the equal and opposite force come into play. The restoring force in the opposite direction, upward direction there. So this restoring force, which is equal to F is equal to mg, okay, will be shared between two springs S1 and S2 there. So if I say F is the total restoring force there acting on the spring system, total restoring force acting on the spring system in this direction now is equal to F1 plus F2. What is F1 here? The restoring force developed in the spring S1, and what is F2 here? Restoring force developed in the spring S2. F is equal to F1 plus F2 there. But in the case of series combination, what was the case there? The restoring force developed in both the spring was same, but here the total restoring force developed in the spring system, which is equal and opposite to F is equal to mg, total restoring force is shared between two springs S1 and S2. That's why F is equal to F1 plus F2 there. So this point to be noted there. So there it was x is equal to x1 plus x2. So but here F is equal to F1 plus F2 there. Okay, now keep on substituting F1 and F2 there. So the total restoring force developed, okay, so total restoring force is equal and opposite to what? Mg. So mg is equal to proportional to displacement. What is the displacement here? X. In all the cases, total displacement is also same. Displacement in spring S1 is also same. Displacement in spring S2 is also same. X, x, x. Keep in mind that. So total restoring force, okay, is equal and opposite to mg. Mg is equal proportional to displacement. So displacement is x here. Proportional constant is kp. What is kp here? The equivalent spring constant for parallel combination, kp there. Okay. Similarly, rotating force developed in the spring S1 is proportional to displacement. What is the displacement? As usual, x. Proportional constant k1. K1 is the spring constant of spring S1. So minus supposed to be there. Everywhere minus is there. I will neglect it. Okay. Restoring force developed in spring S2 is proportional to displacement. It's proportionally constant K2 there. So I got F1 and F2. Substitute here. So total restoring force developed in the spring system is equal to restoring force developed in the spring S1, that is F1, plus restoring force developed in the spring S2, that is F2 there. F is equal to F1 plus F2 there. Okay, substitute for all these things there. So Kpx is equal to K1x plus K2x, or xx get cancels. Kp is equal to K1 plus K2, or in general K equivalent is equal to, if there are many springs, K equivalent is equal to K1 plus K2 plus K3 like that. That means when the springs are in parallel, so the equivalent spring constant is given by adding spring constant of all the springs. Okay, so this is the derivation there. So you have to include the diagram there in your answers there. Okay, so one problem we will solve that. So the problem goes to like this. This is related to the previous article. A mass of 0.5 kg causes an extension of 0.03 meter in a spring, and the system is set for oscillation. That is spring mass system it is. Okay, mass is 0.03, mass is 0.5 kg, and extension produced in the spring mass system is 0.03 meter. Okay, so find the force constant, that is K, of the spring and angular frequency and time period of the oscillation there. Okay, what is given here? So mass is given, extension produced is given, x there. So you know that from the mass you have to calculate the downward force that is acting there. Okay, so F is equal to mg, multiply mass by 9.8, that gives 4.9 Newton there. So you know that. So according to Hooke's law, F is proportional to displacement, or definition of the simple harmonic motion. So restoring force is proportional to displacement. F is equal to minus kx. So minus I can neglect here because only magnitude is required there. So k is equal to F divided by x. No negative sign. Okay, so substitute there. So F already calculated 4.9 Newton divided by x. X already know displacement 0.03. I'll get 163.3 Newton per meter. Okay, so force constant I got 163.3 Newton per meter. Angular frequency, in my previous video came to know that angular frequency in simple harmonic motion is given by omega is equal to root k by m. Okay, what is k here? If it is spring constant, otherwise it is force constant there. Okay, so k divided by m. Okay, so square root of, so k already I calculated 163.3 63.3 divided by m. Mass already I know. Substitute in the formula, I will get 18.07 radians per second. Angular frequency there. What is time period? 2 pi by omega. Omega already got there. 2 pi by omega directly I can do that. But I can substitute in the formula also. Time period is given by 2 pi root m by k. Not k by m by k there. Substitute in the formula, we will get the time period as 0.347 seconds there. Okay, this is one simple problem. So prepare for problems like this. Okay, thank you.